We don't yet understand what went on in the early days of the universe, which isn't surprising given the fact that for a long time we've not been able to observe things at huge distances from us, which we see as they were billions of years ago because light takes time to travel to us. We didn't have any data about what was going on back then because telescopes just couldn't see objects that far away from us. That is, until the launch of the James Webb Space Telescope, which has now allowed us to see galaxies at greater distances than ever before. And those galaxies are confusing us because they're not what we expected them to look like in the early days of the universe, given all of our best theories and models, which again, is not surprising. There's all sorts of new ideas and hypotheses raised to explain what could be going on in the early universe that we haven't anticipated yet. And we've seen that happening this past month when this research paper from McGaugh and collaborators was published, which has been focusing on that overmassive galaxies problem that JWST has found that I've covered on this channel before, including their discovery and some possible explanations for them. Now, McGaugh and collaborators have raised another idea to explain these overmassive galaxies, pointing out that their existence is actually a prediction of a theory known as MOND, an alternate theory of gravity that doesn't need dark matter to explain the universe. Now, I was going to save covering this research until my Night Sky News episode for December this month, but after so many of you online asked me to cover this research, I figured we've got to do this justice. Let's give it its own entire video and dive into all of the details. So, in this video, we are going to cover first a quick recap on JWST's overmassive galaxies problem. Second, what McGaugh and collaborators are claiming can solve this by using this alternate theory of gravity, MOND. And finally, the caveats to this claim and its implications. Like, does this mean that we're gonna have to throw out the idea of dark matter entirely? But before we dive into all of that, Christmas is coming up and maybe some of you are struggling to find that perfect gift for a friend or a family member and might have spotted this beauty on the desk or on the shelves behind me in my videos. This is a Novium Hoverpen and they are just the perfect combination of art and space for a gift, right? It has this beautiful balance of gravity and magnetism. Just look how cool this Hoverpen Interstellar edition looks. It floats in its little dock at a 23.5-degree tilt, which is a nice nod to the Earth's axial tilt, which I love. Plus it comes in either space black, starlight silver, Mars magma, or Neptune blue. Or the premium edition also has a real meteorite shard embedded, which just makes me want one of those even more. Now, as a self-professed space nerd and a stationary nerd, I also appreciate that it's just a gorgeous pen to write with. They're refillable and their Hoverpen Future also comes with an interchangeable tip, so you can use it as a rollerball pen or a gorgeous fountain pen. They just feel so like premium and high-end, and honestly, I just think it's the perfect gift either for yourself or for, you know, the space or stationary nerd in your life this, as the Americans say, holiday season. Even Time magazine agrees. They actually named it one of the best inventions of 2022. So I'm so glad to be partnering with Novium again so that you can use the links in the video description below or scan the QR code to grab one for yourself. Plus, if you use the code Dr. Becky, that's DRBECKY, you'll get 10% off all their hover pens, which come with free international shipping available to most countries. So thanks again to Novium for sponsoring this video. And now let's dive into all of this and start with a quick recap on JWST's overmassive galaxies problem. So, back in March 2023, Labby and collaborators reported that they'd found 6 distant galaxies in JWST data that were much brighter than expected, which I covered on this channel at the time, and in that video I explained how if you've got more light there in a galaxy, then that generally means that you need more stars to account for the amount of light that you see, meaning that your galaxy is heavier, it has more mass. And so what we do is we fit models of how massive these galaxies are to account for the light that we detect. And when Labby and collaborators did that for the 6 galaxies they found, they were far more massive than expected for how distant they were. Now, as I said, because light takes time to travel to us, the more distant a galaxy is, the earlier in the universe's lifetime that we happen to be seeing it. So for those 6 distant galaxies that Labby and collaborators observed, the universe just hasn't been around for long enough to have formed that many stars in such a short time as the time that we're observing them at least according to our best models of the universe, and that's assuming that you have the same efficiency of star formation that you see in the nearby universe around us, which is a big if. And it's why people tend to start doubting those values that you get for the early universe in terms of the mass that we think these galaxies are. These calculations are fraught with pitfalls. Not least because that conversion of the amount of light that you observed to mass in stars requires you to assume some form of distribution, so some spread in the different types or masses of stars that you have in a galaxy. So how many of the heavier, brighter stars do you have versus the much lighter, fainter stars do you have? And we assume that that spread is the same as we see in the Milky Way galaxy, our own galaxy. But that might not be true in the early universe. So a few months later, in 2023, another paper was released suggesting that this could all be explained if that spread of the masses of stars that you have, which is known as the IMF, the initial mass function, just varied ever so slightly. And again, I covered this in more detail in a previous video. If that can change, what it means is that those galaxies that JWST has spotted aren't overmassive at all, and instead they've just formed more of the heavier stars that are brighter, which if you saw last week's video you'll also know is what physics tells us we should expect to see in the early universe. Not only that, but there's another step in between assuming that distribution of the masses of stars and still getting at the mass, because you need to then model for how much light each of those different types of stars or those different masses of stars gives off. And we have a pretty good idea of what that is, what's called stellar population models. But again, they're good, but they're not perfect, right? So there's always going to be some uncertainties in there. So even when these galaxies were first their discovery was announced, people already doubted those masses were as high as Labby and collaborators had estimated. Now, very recently, we also saw this paper by Kurowski and collaborators back in September 2024, which again, I covered in a Night Sky News video at the time. And they claimed there's an extra layer of confusion in all of this as well, because some of the light from those galaxies is actually not coming from stars at all. It's actually coming from the regions in the center around the supermassive black hole that's growing. And that's why the masses are overestimated, because not all that light is actually coming from stars. But this research paper was from the full science team who applied for this big survey with JWST where these galaxies were found. And that meant they had access to the full data set, meaning they could find more of these very massive galaxies in the early universe in JWST imaging. And while they found that they weren't necessarily overmassive, they did find that there are roughly twice as many massive galaxies in JWST's data of the early universe than we should expect from our best model of how the universe has formed and evolved. So clearly something different is happening in the early universe, like stars are forming more efficiently or galaxies are forming faster than we expect. Either way, this data is telling us there is something wrong with our best model of the universe. We just don't know what it is yet, and there's a whole load of possible culprits. And that's really exciting. It means we're going to learn something new. And I think my colleagues and I would have found it very weird if that hadn't been the case, because you've got to remember, our best model of the universe has been developed to match the observations we have from the Hubble Space Telescope and ground-based telescopes that do these big galaxy surveys which can't see as distant, as far back in time as JWST. So JWST was always going to shake things up, we just didn't know how. And now there's all these different hypotheses that have been raised to explain what we're seeing. Which brings me to part 2. What McGaugh and collaborators are claiming can solve this by using an alternate theory of gravity in our best model of the universe. Specifically a theory known as MOND, or modified Newtonian dynamics. Essentially, you take Newton's equations to describe gravity, the ones that we all learn in high school, and you tweak them just slightly for objects that have very small accelerations due to gravity. Now, MOND is technically classed as an alternative theory of gravity because it is not the most widely accepted theory of gravity that best explains our observations of the universe. That still falls to Einstein's theory of general relativity, which describes the effect of gravity as mass, so heavy objects, curving space itself, with space curving more the heavier the object. But the consequence of general relativity being our most widely accepted theory of gravity, because it passes every test that we can throw at it with flying colours, is that on the much larger scales of entire galaxies of hundreds of billions of stars, or even clusters of galaxies, it tells us that there is 5 times more matter that we can't see, that doesn't interact with light, than there is normal matter. We call this dark matter. And there's a huge amount of evidence that's built up over the past century in favour of dark matter, whether that's observational or theoretical or from simulations. Again, I've covered that before in a video if you want to check it out. It covers everything from the speed galaxies rotate at, holding together clusters of galaxies, or colliding clusters of galaxies, and what happens if you simulate galaxies forming without dark matter. But the big challenge to dark matter is that particle physicists, with their big model of what all the stuff in the universe is made of, don't have a particle that could explain like the behavior that we've observed dark matter having, and they've never been able to detect like a new particle outside that model that could explain dark matter, which is why many new, alternate theories of gravity have popped up over the years that don't need dark matter on these huge scales to explain our observations of the universe. Again, I've made a video on this before covering a few of those different theories, but probably the most well-known of them is MOND, which was first published in 1983 by Milgram. Now, I have many colleagues in research institutions and universities around the world that are looking into these alternative theories of dark matter. This is not fringe science, this is not being swept under the rug in any way. Alternative theories of gravity that do not need dark matter are actively being researched and shouted about all the time because we want to figure this out. Now, because of this, it means that we know very well which observations of the universe MOND can successfully explain, like galaxy rotation curves, for example, and which ones it can't explain, like the wide binary test with Gaia data, which I covered in a video on my channel last year. If you want a real astrophysics deep dive into this, I highly recommend this fantastic review paper by Bannock and Zhao from 2022 that reviews all of those successes and failures of MOND. And of course, we do the same for general relativity as well, and at the minute, more evidence has come down on the side of general relativity than it has for any other alternative theory of gravity, which means the evidence has also come down on the side of dark matter existing in the universe. So, our best model of the universe is known as lambda CDM. Lambda for dark energy, what's causing the accelerated expansion of the universe, and CDM for cold dark matter. And the properties and the parameters that we get out of that best fit model to describe the universe, like for example, the age of the universe, are that best fit because it's been fit to the observations of the universe we had so far with the likes of the Hubble Space Telescope, which were obviously much closer by than what we could observe with JWST. So who knows, JWST could now change all that. And that is what McGaugh and collaborators are now arguing that we have evidence for from JWST data. Because these overmassive galaxies that people have been identifying were actually predicted to exist by MOND over a decade ago. Now, interestingly, they don't mention the Kurowski paper from the Sears science team in this research. Perhaps that research was published too late for them to include in this one in terms of like the publication timescales, but they do include a lot of other data from JWST studies on their plots. So for example, here we have redshift on the x-axis. That's essentially a measure of how far the light has traveled through the universe, so it's a distance indicator, right? But it's also a time indicator as well. So how early in the universe are we seeing these galaxies? And then on the y-axis, you've got the mass of the galaxies that have been measured, which as we heard earlier, it's a bit of a woolly measurement because of all the assumptions that go into it. Now, the dark grey region is where our best model of the universe, lambda CDM, completely rules out that any galaxy should exist there. It's not physically possible to create galaxies that big because there's just not enough stuff to be able to make them in the first place. The light grey shaded region is where lambda CDM says it's unlikely that galaxies form that large at that time, but it's not impossible. And then these red and blue lines are growth tracks for the heaviest simulated galaxy in a given, simulation of the universe, again, that uses lambda CDM. And McGaugh and collaborators point out there's a bunch of galaxies that are still too massive for lambda CDM to explain. Here's that exact same data again, plotted in a different figure in their paper, but this time shown over a bigger time period, and includes some galaxies closer to us as well. Again, those red dashed lines are growth tracks of a single galaxy in a simulated universe, right? Again, the simulation uses lambda CDM, where galaxies grow in the universe hierarchically, so they merge together. The smallest ones form first as gas collapses down, and then they merge over time to steadily give you bigger and bigger galaxies. Whereas the solid black lines in this plot are more like what you'd expect from a theory like MOND. Now, really important caveat here, those black lines aren't a direct prediction from MOND, because nobody has yet managed to make a cosmology, so a model of the universe, that uses MOND as the theory of gravity. What they've actually plotted is a massive oversimplification of what you might expect with MOND. What they've actually plotted is something known as a monolithic model. Essentially, you immediately form a massive galaxy that then just grows at a slower rate over time through star formation. There's no hierarchical merging required like you get in lambda CDM, which we don't know if that's like a physically good explanation or not. It's literally just like the most simplest toy model you could assume. Let's just assume galaxies form massive and go from there. And I think if you just looked at these plots with no context and without the rich history of knowledge that comes from working in this field that I have tried to impart over the last 10 to 15 minutes of this video, then yeah, I think you would go away from this paper assuming, yeah, JWST has convincingly come down on the side of MOND, like in favor of MOND, which is a conclusion that even the authors of this research paper don't fully support yet. Which brings me to section 3, the caveats and implications for this result that's been presented by McGaugh and collaborators. Let's start with the caveats and look again at that first plot that I showed from McGaugh and collaborators. First of all, we already talked about how these masses that are plotted on the y-axis are most likely overestimates. Because of our assumptions on the IMF and the star formation efficiency and stellar population models, and some light might be coming from growing supermassive black holes. So it's likely that these points will all shift down by some currently unknown amount. The second caveat I want to point out is that only the data points plotted in black have redshifts, i.e. distances, that we can properly trust. So this is where you measure how much the light has been stretched out by, redshifted by the expansion of space to work out, okay, how long has it been traveling through expanding space for? And the black points have been done using spectra. So you actually take the light from a galaxy, split it into a prism, and you get much more precise measurements of how much that light has been shifted by. But all the white and the colored points here have redshifts measured just from images, which is nowhere near as precise. It again takes a lot of modeling of the light given out by the stars to get at, and in fact in the models they're degenerate with the mass that you infer, which is what's plotted on the y-axis. So that means that we expect some of these points, not necessarily all, but some of them to actually shift to the left here, to lower redshifts. The next caveat is then about the two lines that are plotted here, the red and the blue ones, that are those growth tracks for the heaviest simulated galaxy in a given simulation, again that uses lambda CDM. You remember these are the growth tracks. You pick out the heaviest galaxy that you've been able to create in a simulated universe that uses lambda CDM, and you see, okay, how massive does that get at all of these different redshifts or times in the universe's history. These also highlight something interesting, because the blue line is from what's known as the TNG 100 simulation, and the red line is from what's known as the TNG 300 simulation. The 300 simulation is much bigger. It simulates a much larger volume of a simulated universe, which means you're more likely to get rarer things, like more massive galaxies that are possible in lambda CDM, but not as likely, the tail end of the distribution, i.e. the light grey shaded region. If you got awarded the insane amount of supercomputing time that it takes to run these huge simulations and pushed it to like TNG 600 or TNG 900, would you shift that line of the heaviest simulated galaxy up again, coming closer to matching the JWST observations? Which, let's remind ourselves, are also intrinsically biased, because at those huge distances, we're only ever going to be able to see the biggest and the brightest of things. The weirdos at the extreme ends of the population, right? The tail ends of the distribution. And all of those caveats also apply to this second plot from McGaugh and collaborators that I showed, which I also want to note that this plot can be a little bit misleading to a non-expert, because the x-axis, the redshift axis, is not actually linear in time. Look at the cosmic age axis at the top here, which puts things into perspective. Less than redshift 6, which is what's been added here compared to the previous plot, covers 13 billion years of evolution, whereas greater than redshift 6 covers 800 million years. But what I think this plot really clearly demonstrates here is how our best model of the universe, lambda CDM, has been calibrated on the observations we had before at lower redshift, closer to us with the likes of the Hubble Space Telescope and also with JWST as well. Since those red lines from the galaxy simulations, this time from Illustris here, do a pretty good job at those lower redshifts, but not at high redshifts. At least as it looks here compared to the solid black lines. But you've got to remember, those black lines aren't direct predictions from MOND. They're not simulations with MOND. They're just a gross oversimplification of the extreme of what we'd expect from something like MOND. So you cannot just take either one of these plots out of context and jump to JWST falsifying dark matter. We just don't have enough evidence to claim that. At least not yet, anyway. And McGaugh and collaborators are very clear in their paper when they discuss all of these JWST results, what that could mean in the context of everything else that we know. Either sticking in this lambda CDM scenario where maybe you just have, a different star formation efficiency going on in the early universe, or maybe galaxies do actually form ever so slightly differently. Maybe there's not as much of a stress on this hierarchical structure formation. You could just get galaxies forming very big early on, again, still using like GR rather than MOND. But what I find really interesting is that they give sort of like another way of testing whether it, is it MOND or is it GR with lambda CDM in the early universe. And the one I want to highlight is for all of you that watched last week's video on reionization in the early universe, because MOND predicts an earlier onset time for reionization. And so in their conclusions, McGaugh and collaborators, they lay out all the evidence they've collected from JWST and then the predictions that MOND makes, but again point out we don't have a cosmological with MOND yet like we have for lambda CDM, which means we can't make any concrete predictions with it. But clearly, the data from JWST is telling us that something is wrong in our models. We just can't figure out what that thing is yet. And that is really exciting, right? This is science happening in real time. And as more data is collected, there'll be all these different hypotheses that are popping up, arguing for one idea over another, despite the fact that we don't have all of the puzzle pieces yet. But slowly but surely, as more data is taken, we should get a better idea of what's going on in the early universe, and hopefully collect enough evidence to say for definite which idea the observations support best. A universe with or without dark matter. I got hair up my nose and it really distracted me. Who's afraid of little old MOND? You should be. I'm always so conscious of saying like JWST so quickly because like it's just something I say so often that I get people emailing me like, what are you saying? Are you saying like JUST? Or no, I'm just saying it really fast, okay? Because you say it so often and it's just one of those things. You're just like JWST.